Hi all. In this session, we are going to learn about IP addressing and what is the need of IP addressing in computer networks. First, let's understand what is logical addressing that will take place in the network layer. Any network device has a physical address called a MAC address, which is assigned to the device at the factory during the manufacturing process. We have learned about MAC address in the last module. Logical addresses are created and used by network layer protocols such as IP or IPX. The network layer protocol translates logical addresses to MAC addresses. Different types of IP addresses are IPv4 and IPv6. IP means Internet Protocol version 4 and IPv6 is Internet Protocol version 6. IPv4 is 32-bit addressing scheme, whereas IPv6 is 128-bit addressing scheme. Let's learn about IPv4 and IPv6 in detail after some slides. First, let's understand what is the need of IP addressing in computer networks. Suppose there is a computer in the network. This is a network. Inside this network, there is a computer which is called as a host system. Inside this computer or inside this host system, there is a process we have to execute. For example, we are typing www.google.com in the web browser. So we want to connect with the server of google.com, which is situated in either in US or Europe or any other country or in any other network. So what will happen here is, first our process should identify to which network this Google server is there, and inside that network which is the host ID of that particular Google server, and inside that Google server which is the process that is requested. So we have to first identify the network to which the particular process belongs to. After that, it should identify the host or the server to which it belongs to, and after that it should identify the process. For identifying the process, we have to use port number. There is different port number for different processes. So in order to communicate from our computer to the Google server, first our computer should identify the network ID to which the Google server belongs to, and then it should identify the host ID, then it should identify the process or the port number. So this is the three steps that will take place while we are trying to access a web page through the computer network protocol. In order to identify this network ID and host ID, we are using IP address. And IP address consists of network ID and host ID. So when we type www.google.com, what will happen is our computer will first send this web URL to the domain name server, DNS server, and the DNS server will translate this address into IP address. So it will identify the corresponding IP address of google.com, and then it will establish connection with that particular server by identifying the network ID and host ID from that IP address. So if we are trying to access a website for the first time from our computer system or from our host system, it will take some time to load. Why this additional time is, it will first send the web address or the URL to the DNS server to identify the corresponding IP address. Then it will establish connection with that IP address and it will load the web page. For this process, it is taking this much time. So this delay in loading the web page is called as overhead, DNS overhead. So what the computer will do to reduce this DNS overhead is, whenever it is getting the mapping with the URL with an IP address, it will save that IP address in a cache in our system. So whenever we are again trying that particular URL, it will directly load from the cache. It will keep updating the cache whenever we are getting a mapped IP address from the DNS server. This cache will be updated frequently. So when we are trying for a URL, first it will check in the cache of our system for the corresponding IP address. If it is not available in the cache, then it will send the request to the DNS server. From the DNS server, it will provide the appropriate IP address. Then it will store that IP address in the cache and it will load the appropriate website. So this is what is happening while communicating between two computers through network using logical addressing scheme. Next, let's learn about Internet Protocol or IPv4. Internet Protocol is one of the major protocols used in the TCP/IP protocol suite. This protocol works in the network layer of the OSI model and the internet layer of the TCP/IP model. Actually, the main aim of using the IP addressing is to uniquely identify each of the hosts in a network. So the Internet Protocol provides a mechanism to uniquely identify hosts by an IP addressing scheme. IPv4 uses 32-bit logical address to uniquely identify a system. Let's see the typical packet format of an IPv4 system. The packet format is shown here. The width of the packet is 32 bits. The first one is version. Version represents the version of the IP that we are using. Usually this is the packet format of IPv4. So the version number will be 4. So the binary of 4, which will be 0100, will be the version number here. Next is header, which contains the length of the IP header, which helps to know the beginning of the data that is being sent. Next is the type of service, which is of 8 bits. It is used for the quality of the service, QoS. We will learn about QoS in the 5th module in detail. Next is total length, which contains the total length of the datagram that we are sending. And the next field is identification, which is used for identify the fragments of an original IP datagram. As we all know that in network transmission, the data is divided into various fragments and each fragment have a unique identification number. This number is useful during the reassembly of the fragment at the receiver end. So this identification can be done with the help of IP datagram. So this field will help to identify to which IP datagram the fragmented datagram belongs to. So while we are dividing the data into fragments, we will provide some unique identification numbers. That details are provided in this 16 bits. Next is DF bit, that is do not fragment bit. If the DF bit is set as 1, then it indicates that the intermediate devices should not again fragment the IP datagram at any cost. They should not again defragment the data message. Next is MF bit, which is more fragment bit. If the MF bit is set as 1, it indicates that more fragments are following. Next is fragment offset, which indicates the position of a fragmented datagram in the original unfragmented IP datagram. For example, if we are dividing a packet into 5 fragments, then we will provide the number as 1, 2, 3, 4, 5 for each fragment. So the fragment offset of this particular datagram will contain the fragment number in the original unfragmented IP datagram. Next is time to live TTL, which indicates the maximum number of hops a datagram can take to reach the destination. For example, if a data is traveling from the source to the sender through 10 nodes, then definitely it should take 10 hops, which means it should go through 10 different nodes and so that it should reach the destination. So whenever it is passing through each hop or each node, then the TTL value will be decremented by 1. So this can be used for preventing the IP datagram from looping around forever in a routing loop. How this is achieved is, it is decremented by 1 when it passes through an intermediate device or a node. If the value of TTL becomes 0 before reaching the destination, then the datagram is discarded. Next is the protocol, which tells the next level protocol at the network layer at the destination side. The protocol number will be different for different protocols that is used in the destination side. For ICMB it is 1, for IGMB it is 2, for TCP it is 6, and for UDP it is 17. Let's learn about all these protocols in detail in the upcoming lectures. Next is header checksum field, which is a checksum value used for error checking of the header. Next is the source IP address, that is the IP address of the sender system. Next is the destination IP address, which is of 32-bit, which is used for identifying the destination system. And next is options, which is used for special purposes like recording the route from the source to the destination. Padding, that is adding additional bits to make it compatible with the packet format. All these details will be provided in the option section. And the next part is the data, where which the original data is transmitted from the source to the destination. So this is the typical packet format of IPv4. Next, let's see the packet format of IPv6, that is Internet Protocol version 6. IPv6 is 128 bits. Here also version is there, which indicates the version number. Though we are using IPv6, its value will be always 6. Next is a traffic class, which is of 8 bits. The traffic class indicates class or priority of IPv6 packet, which is similar to service field in IPv4 packet. In IPv4 we have learned about type of service, which is an 8-bit field used to identify the which type of service or the quality of service we are providing. Here the traffic class is similar to that. We are using to identify the type of service it is provided. It helps routers to handle the traffic based on priority of the packet. If any congestion occurs on the router, then packets with least priority will be discarded. Next is hop limit, which is same as TTL in IPv4. In IPv4 we have learned about TTL, which indicates for the number of hops a datagram can take to reach the destination. Every time when it passes through a particular hop, the value will be decremented by 1. If the hop value is 0, then the packet will be discarded. So hop limit is the maximum hops that a packet can travel. Next is a payload length. Payload length tells router about the amount of information a particular packet contains. The next field is next header, which indicates the type of extension header. Next is a flow label. Flow label field is used by source to label the packets belonging to the same flow in order to request special handling by intermediate IPv6 routers. Next is source address, the address of the originator of the packet, and next is the destination address, which is of 128-bit, which is the address of the intended recipient or the receiver side address. So this is the typical IPv6 packet format. Thank you.